Okay, guys, today we're going to be going through our last chapter, yeah? P2, Planning, Analysis, and Evaluation, yeah? Any questions before we get into it?
I'll go to the toilet.
Andy, you can't just be going out of the classroom like that, man. You gotta ask me before you go out, yeah? Alrighty, I guess, let's get started, yeah? So I'm assuming you guys read your books because if you did, you would know that this is literally the first page of the chapter. Yeah? So I won't be going through this part into too much depth. So let's begin, huh? Yeah? So when going into your practicals, you want to be sure to read through the instructions. I can't stress this enough, fellas. I've seen it all, folks, where I've had students from the previous batch coming to me and saying, Mr. Mike, that practical was way easier than the stuff we actually did in class. And when the test results come out, they get a big fat 0, yeah? Again, I can't stress this enough, guys. Read the instructions. It'll go through on how to carry on with the procedure, the measurements and units that are to be taken, and the data you need to be recording, as well as the safety measures that should be taken, yeah? Understand? So then let's get into the next section. When conducting your experiments, you should be able to identify the independent and dependent variables. Now you're probably saying to yourself, what are independent and dependent variables, Mr. Andreas? Well, I'll help you answer that. God, I'm a comedic genius. So let's say, for example, we have a goldfish, yeah? And you want to see if the circumstances of growth is relative to the amount of sunlight you give it, given the same circumstances. So maybe same fish bowl, same type of water, same pH in the water, and same type of food given. But the difference being how much exposure to sunlight each fish gets. The latter is going to be your independent factor, yeah? The one you are isolating and in control of, yeah? Now the dependent variable is pretty much the changes that occur when you adjust your independent variable. So if we're talking about our goldfish again, we're trying to see its growth rate relative to the amount of sunlight it is given when everything else is constant, yeah? Its height, width, color, anything that could be physically seen, yeah? Those are things that change by themselves when we change the independent variable, hence the term dependent. It relies on other factors for it to activate. There are also other things to take note of, such as the method you will use to control the independent variable, how and what will you measure, how and what will you change, as well as how will you keep this variable constant while others are controlled. Smooth sailing, right, guys? You understand all of this? You should, because I'm the best teacher. Okay, so next is the safety measures you should be taking in order for you to conduct your experiments without harming you or your classmates, yeah? Like, protect yourself accordingly. Like, for example, wear some sort of insulator if you're experimenting on circuits. Wear goggles and lab coats, self-explanatory stuff. Stabilize your apparatus in order to prevent you from knocking it and spilling liquid everywhere. Be sure to switch things off when you're not using them. And most obvious, but not obvious point, don't do anything unless said or otherwise told to do so. Come on, guys. You're 18. You should be able to understand when someone tells you not to do something. Alright, now we're getting more into the stuff that really matters, yeah? Stuff that you do after everything mentioned previously, yeah? You start doing your experiment, start to record your data, but none of that really means anything unless you know how to analyze it and put it into real-world use, yeah? You should be able to plot your data into graphs and describe what is going on in the graph, yeah? Showing what's on the X and Y axis, respectively. Afterwards, be able to come up with a conclusion as to why the graph looks the way it does, and maybe, giving points and recounting everything you have done in the past, hour or two of experimenting. Generally speaking, the graph should be diagonal and straight, no curves or bends, generally indicating that you're doing something right here. But in most cases, just looking through every practical that all of you have done, it doesn't start or end like that at all. And you should give, again, explanations as to why the data looks like that. Maybe because of faulty or unideal apparatus is being used, or variables that were literally out of our control. The weather maybe, or maybe a fire broke out and ruined things. Anything can be said. Something that is plausible in the lab is something that should be listed and written down, as long as it's something that occurred in the experiment. Yeah? You guys got any questions before we go on? I mean, it's not like you guys say anything anyway, so I'm just gonna go ahead and move on to the next slide. So you guys, I'm just gonna ask, have you guys learned this in math class yet? I don't learn math, and I gotta ask, what the hell is this? Come on, man, you need to, learn math. Math is everything, dude. That's why I'm the best teacher. Okay, I'm gonna make this short, because this isn't math class. All you gotta know is that logarithms makes calculations easy. That's why it was devised. Before the advent of calculators, we used logarithms. So let's say, for example, let's do a basic statement. Logarithm of 1,000 is 3. What does that mean? Well, what I mean by this is when 10 is raised to the power of 3, it equals 1,000. So 10 is used as a factor 3 times. Now let's do that in a more mathematical method. Log 10 in brackets 1,000 equals 3. If we consider the base to be 10, we can say base 10 is raised to the power of 3, and we get 1,000. Get it? Yeah, most definitely, I understand. Well, alrighty, if you do, then in short, we have two graphs, y equals axn and y equals aekx, and we have to use two types of logarithms, ln and lg for them. If you want to know how and when to use those logarithms, just look at the book on table 2.1. Yeah? And lastly, guys, we have uncertainties. Yes, your guys' favorite. We all love uncertainties. You guys are probably already familiar with these already since we discussed this chapter in P1 last term, but you know what? Because I'm Mike Andreas, let's go through it anyways. We can use uncertainties in tandem with our graphs to get more precise measurements. Not accurate, but more precise. Remember, guys, it's more important to have multiple recordings that are in the same realm of each other than it is to have multiple recordings that are far apart from one another. It'll show the consistency in your methods of measuring. Also, keep in mind that our measuring apparatus will always have something wrong with it, and thus it's always good practice to keep in check and write down its absolute uncertainty. Generally speaking, our rulers and our stopwatches will always have a plus or minus 0.01. It's good to give this kind of data out along with your recorded data because it ensures that our measurements could be correct above or below a certain increment. So let's go through one problem first. So here we have a graduated cylinder with water in it. And what we want to do first is that we want to be at eye level with the water. And also, in order to find the closest measurement, we got to look at the meniscus of the water. Just by looking at the meniscus at eye level, we could say that it measures around 7.8 milliliters of water. And so now we must look at the smallest division given by the apparatus. And in this case, it's 1 milliliter. Now we divide it by 2, and thus it gives you an absolute certainty increment of plus or minus 0.5. As for our percent uncertainty, it's as simple as taking our absolute uncertainty and dividing it by our given or our found measurement and multiplying it by 100, and in this case it gives us 0.7%. And in short, that is a pretty shit measurement. It's also worth noting that uncertainties aren't just only meant for measuring apparatus and can be used in graphs as well in the form of error bars and error lines, as each data point will have two uncertainties associated with it, an uncertainty from the x value and an uncertainty from the y value. Here's a graph that shows a good example of how error bars are drawn in. For this graph, the error bars for the y value are much larger than those for the x value. Often the uncertainty in either the x or y value is so small that error bars cannot be properly drawn in. In this case, the uncertainty in x can be ignored. It is, however, important to make a note in your report if you do this, yeah? Here's a graph with both error lines and error bars drawn in. The blue line represents the maximum, or in this case, the steepest possible gradient, and the red line represents the minimum, or in this case, gentlest possible gradient. Both of these lines should pass through all of the error bars on the graph. The value for the final gradient will be the average of the maximum and minimum gradients. And the uncertainty will be half the difference between the maximum and minimum gradients. So there you have it, guys. That's chapter P2, the final chapter in our physics course. Do you guys feel any smarter by the end of this class?